So let's move on and let's talk about solving ux equals b, where u is an upper triangular matrix. And again, how does this all fit in? Well, in the end, we're left with having to solve an upper triangular system, and obviously this is an upper triangular system in disguise. With a little bit of luck, the algorithm that pops out mimics exactly what we do in back substitution. Now, we probably don't get enough into that here for you to see that, but if I recall correctly, the notes actually lay them side by side and explain why they are one and the same thing. So here we have U, and it's an upper triangular matrix. We're interested in solving ux equals b. Now, in the bigger scheme of things, this actually is what comes out of solving ly equals b, so you could think of it that way. But what we call that vector in isolation doesn't really matter. This is the same as solving an upper triangular system of equations. So we do exactly what we did before. We slice and dice. We're good at slicing and dicing. We love to slice and dice. So we slice and dice u, we slice and dice x, and we slice and dice b. We want to solve ux equals b, so what we do is we substitute in the partitioned u, the partitioned x, and the partitioned b. And what we get is this right here. And then if we multiply this out, what we get is this right here. So if we then set what's on the left of the equal sign to what's on the right of the equal sign, what we find is that this is beta 1, and u22 x2 is equal to b2. So let's move that over here so that we can talk some more. Okay, now here is where things become a little different. Think about how we did back substitution. What really happened was that we had solved for a whole bunch of the unknowns already. As a matter of fact, we started at the bottom when we had 3 equations and 3 unknowns, and it was upper triangular. What we did was we solved for chi2 first, and then once we knew what chi2 was, we substituted it in, and we solved for chi1. And once we knew what chi1 and chi2 were, we substituted those in, and we ended up solving for chi0. So we're going to mimic that here, and the way we're going to mimic that here is we're going to say, well, what if we have already computed x2, and what if that has overwritten b2 so far, and no other computation has yet happened? That puts us in this situation right here, where b2 holds x2. So that means that we know what x2 is. If we now substitute in what x2 is, and we solve for chi1, then we get this right here. And we can either leave the x2 there, or we can put in b2. Now let's look at this a little bit more carefully. This is the right-hand side with something subtracted off. And then in the end you divide by the appropriate coefficient in your upper triangular matrix. That's very reminiscent of what we did when we substituted in. We subtracted all the terms that now we were known from the right hand side, and then we divided by the coefficient that remained and multiplied the unknown that we were trying to solve for at that point. Go back and look very carefully at back substitution, and that's what you will find. So the algorithm that then comes out is this one right here. And the algorithm is march through the matrix and the vectors. If you look very carefully, you notice that the thick line is here and here, and that actually we are marching through the matrix in that direction. That's because we compute the last elements of x first, overriding the corresponding elements of b. And in the current iteration, we update with the final result that element that's being exposed there, beta 1, which is now actually the last element of the top part of b. What do we do there? We update it as such, and what you notice is that that's a dot product. As a matter of fact, we have this lav.s routine that would be just perfect for that computation. And then we have to divide beta 1 by epsilon 1, which is the current coefficient in u that's exposed. Now we have an algorithm for solving ux equals b, which is the same as back substitution.